Hello everyone and welcome back. In this episode we are implementing our fixed joint. In the last episode we added a list to make sure that specific objects are not colliding with each other. And in this, because we need that functionality for our fixed joint and for our hinge joint. And the fixed joint is the topic for today. Alright, then let's jump to Visual Studio and create a new joint. This folder, file new, and I call it fixedjoint.js. There we go. Then, of course, we need the class. It's called fixedjoint, extends joint. It's gonna have a constructor with just a connection. There we go. Oh, and as you see, I have GitHub Copilot on again, so I'm gonna disable that. There we go. And now we can set up our fixed joint. We need to do some things here this time. First, I'm gonna say this dot Richie A is this dot. I think I can copy this line from the other one. No, I cannot. All right, then let's do it like this. I'm gonna say joint connection dot rigid body A, and the same thing for the other body. There we go. Then we are taking Richie A and saying we're not adding. We are adding the other body to the non-colliding objects. So Richie A and Richie B are not colliding. And we do this by add non-colliding Richie. And this is going to be Richie B. There we go. And we're gonna save our anchor position for A and for B. So this joint connection dot get anchor position, and the same for the other one, anchor B. And oh yeah, and I think I made a mistake there. Yeah, that it's called anchor A position and anchor B position. All right, and then I'm gonna save the initial length between those anchor positions. This is used to move the anchor to its position. When one shape is moving, then the other shape needs to move in that direction too. And with that initial length between those, we can say which distance they are apart from each other. And if it's smaller, then it's going to be corrected. All right. Yeah, initial length is the subtraction from anchor A with anchor B, and then we take the length of it. All right. Then I'm going to store the material properties. So Richie A, I'm not quite sure if I renamed it to restitution. I think so. Restitution. Let's look at it again. Material, restitution. All right, I renamed that. Restitution, yeah, I think it's right. Yeah, and this is Richie A dot material dot restitution. The same for the other body. There we go. and for Richie B. Cool, cool. Then I want to store the friction too. So Richie A friction is this dot Richie A dot material dot friction, and I'm gonna store the friction for the other body too. Trivial dot friction. There we go. Why I'm doing this? It's because we are going to do a little of a positional correction and a resolve collision step in our update connection methods. And while doing this, I don't want to have a friction and a restitution of these bodies. So there's no jumping around. I'm going to set this to 0 and there will be no friction between those. That's why I don't want to have a frictional impulse between those. Yeah, and then I'm going to calculate the relative orientation. So this dot relative orientation, because a fixed joint usually, you know, a body with a connected with a fixed joint to the other body, usually tries to stay at the same angle to each other with the same rotation. That's why I need to store the relative orientation to move it to the right, well, to the right orientation again. And this is this dot a rigid body b dot let's say get shape dot orientation, and I think I don't have orientation. I'm gonna add this one in a second. Then I need to add Richie A dot get shape dot orientation. There we go. Maybe it's, I think we called that rotation, maybe. Let's see. Rigid body in the shape. Yeah, there we go, shape. Okay, I'm gonna take a look. I'll be back in a second. Yeah, I found that. We have to declare a new variable, and this will be called orientation, of course. So this dot orientation is equal to null 0, and then I'm gonna go down to the rotational part, and here I'm gonna say this dot orientation, oh hoppala, orientation plus equals radians delta, and that's everything we need. All right, then we can go back to our joint. That's our relative orientation, and then I'm gonna set joint iterations, because we are doing some, like in the simulation class, when we are doing multiple iterations over the solving process, we're doing the same for the fixed joint. The more we do, the more stable it will get, or yeah. And that's our joint iterations. Oh, I forgot an S here. There we go. And then of course we have our update connection A, which gets a delta time. And then we have, of course, the other method too, update connection B. I think there was a delta time, right? No, there wasn't actually. Do I need that delta time? Not quite sure. I'm just gonna remove it for now, and I'm gonna add it if I need it. Okay, and then I have two more variables. One is called restore material, and here we are just saying all these values are going to be well, restored. So RichA.material dot restitution is the restitution we saved earlier, so this one, and for the other shape, of course, too. And then we have the friction also. You have to do that for the friction also, too. Yeah, friction, there you go. Friction, this is GB. Then here it's rigid A friction and rigid B friction. All right. Yeah, that's right. Cool. And then we have the same thing, but for setting the material to 0. And here I'm gonna say 0, 0, 0, and 0. Cool. And now I'm gonna say that I want to set the material to 0. So let's start set material 0. And now I'm gonna iterate through the joint iterations. So this is going to be I smaller than this dot joint iterations. Not interactions. Joint. I wrote interactions. Oh my. I mean iterations. There we go. All right, and then I plus plus. Okay. Now I get the current anchor position from body A. This is this dot joint connect. No, joint connection. Get anchor position for A, and we need to do the same thing for B too. I actually could copy that simply from above, but well, anyways. Now I'm gonna calculate and get a direction vector between those anchors, like we did right there. I can copy this one, and I'm gonna say anchor there is the subtraction. Then the distance. Oops, the distance is the anchor there. Distance. Oh no, length. It's actually called length. There we go. And then if the distance is too small, like this small, then I'm gonna say break. Okay. Then I'm gonna normalize the anchor direction. So normalize. I'll get a copy. And then I'm gonna create something maybe weird. I'm gonna create a collision manifold. And with this collision manifold, I can resolve this collision. I'm simulating a collision. And we use this collision to fix our rectangle into one position, so I can't escape this one. It's like an inverse collision resolving step, kind of. Yeah, and we can do that by saying contact is a new collision manifold. collision manifold. Yeah, the depth is 0, the normal, and then the anchor position for B. Then the rigid bodies for that contact. Contact rigid A is listed rigid A, and the contact for rigid B, I mean I need to set these two rigid bodies too, so just simply set it like this. And then I can say if the distance is greater than this initial length, then I can say the contact or depth value is distance minus listed initial length. And then I have the depth value, how much the rectangle will move in that direction or out of that direction. Yeah, it's like a spring kind of. It's trying to get to its resting position. Then I have a else case too, and this is going to be contact of depth is listed initial length is minus distance, so it's basically the opposite direction, okay? And then also I have to normalize, sorry, not normalize, I mean scale the normal with -1. So it's like it's actually really like the spring. It's larger than the initial length, it's trying to go the other way to its rest distance, and if it's smaller, it's again trying to get to the rest distance but in the opposite direction. Yeah, that's basically what we're doing here. And now I can say contact dot positional correction and contact resolve collision. Okay, and that's for update connection A. And now we can restore the material again. But first, yeah, what I forgot is we need to do the same thing for the orientation. So for the orientation, it's not going to be a collision step. Collision step is only necessary to hold that rectangle in place, but we can't say, okay, now please hold your angle in place, right? And we need to do this a little bit different. You can do that by saying the current orientation difference. And this is, well, it's also kind of the relative orientation. We're trying to maintain the relative orientation. We can do this by saying this dot rigid B dot get shape dot orientation minus the same orientation but for rigid B, rigid A, I mean. There we go, orientation A. And I'm also going to add a really, really small number. Well, not that small number. The really, really small number is this one. When I say 0.01, just a small bias. And then I'm saying the orientation velocity. So the fixed orientation velocity, velocity is just that relative orientation minus the current orientation difference. Okay, so I'm calculating a velocity out of that, where we're gonna send it in this direction. So we are adding this to the angular velocity for Ritchie body B. So this one, angular velocity plus equals the fixed orientation velocity. I'm gonna say 0.5 because it's again the half of it, because we're doing the same for the other connection too. And I'm also saying times 0.1 because it's just a small rotation, and with the update loops, with the joint iterations, it's going to be stronger. You know, when we're taking a higher number, then it's getting unstable, unfortunately. So this fixed joint is not really kind of a fixed joint, I must admit, but it's going in that direction pretty good. Yeah, and then we can restore the material. Restore material. And there we go. Now we have our code for update connection A, and now we can do the same thing for update connection B, and we just can copy this one and making sure everything's right. Alright, so this looks good. This looks also good. I think this one needs to be flipped. Yep, let's flip that. There we go. This looks good. This looks good. This too. Anchor direction. Alright, this is also fine. This one is also fine. Maybe. I'm not quite sure if that must be A, but let's try I'm gonna try and change that to anchor A. Alright, this one looks good. I think this one looks also fine. This is also fine. The orientation. I think, yeah, that must be A, of course. And this must be A2. This must be B. All right. Yeah, I'm gonna take a look again, see if I made any mistake, because I'm sure I made a mistake somewhere, and I'll be back in a second. All right. It seems it's looking pretty nice. Yeah, let's go to the simulation class, because we need to change some things there too again. We need definitely at least one rectangle, and here I need to get a anchor ID. So anchor rect ID is equal to rect dot create anchor. This will be a new vector with the coordinates of 75 and 0. Then we have the rect rigid body. I'm going to give it a mass of 1, and then we're going to push it. And yeah, the anchor ID, we are going to use this one for our fixed joint connection. But we need another rectangle. I'm just going to copy this one. Say rect2. This one will have the coordinates of 600 and 200. It's going to have a width of 300 and a height of 25. Then the coordinates for it will be minus 125. This will be rect2, and this rigid body will be named rect2 rigid body. Also, the anchor will be anchor rect2. Then I can push this one to the rigid bodies. Alright, and that's our rectangle. And I think I'm also doing something with the circle. Yeah, I'm gonna change the coordinates of this circle to 400 and 300, radius 60, it's fine. And then, well, actually, we are not needing the circle right now, so I'm just gonna let it be. Yeah, then we have our join connection. We can uncomment this one again with the rect rigid body, the anchor rect ID, and we will have the rect2 rigid body here and the anchor rect ID there. All right, and I think now we're ready to test if it's working. Yeah, I just saw we are not ready to test it because we need to change this one to fixed joint. Then we're only gonna have that joint connection in there. Okay, that's good. Then we have to add our fixed joint to our scripts. This will be fixed joint. There we go. Okay, I think now we are ready. Okay, I figured some things out. You have to add here the super, and I also spelled that joint connection wrong. It must be joint connection, not join connection. There we go. Okay, yeah, also, I think we can remove this and this because this is already available in our parent class. So let's say I'm gonna do this one and this one. And I think this should be right. Rect rigid body. Incorrect. This is the right one. Incorrect too. Oh, that's wrong. That must be rect 2 there. All right. Good. Yeah, I also forgot. We can remove this one too, because we have that in our parent. Okay. All right. I think we can now go to the browser, save, and refresh the browser. Yeah, I need to switch to the browser, and seems like we don't see anything. What I'm going to do is I'm gonna remove the circles now, because I think they are a little bit, yeah, just coming in the way. So let's remove them. Okay, there must be something wrong with the joint. Yeah, these are our shapes, which should normally be connected with each other. Oh, I forgot that, yeah. Yeah, I'm gonna take a look and I'll be back. Alright, so the first thing we need to change is something in the coordinates. I confused these two numbers. That needs to be 400 and 200. And now these objects are now directly next to each other. And then we have to Alright, hello everyone, welcome back. Yeah, I found the error. The reason because our objects are vanishing is because of a division by zero error. And if we look at the collision manifold and in the resolution step, we are calculating the restitution. And here we were taking the summation of both restitutions, but in our case we're trying to set it to 0, and this will be 0, and then we have a divide by 0 case, and we can't do that. Same thing for friction. What I did now is that I changed in the fixed joint, I changed this value from 0 to 0.0001, and yeah, that's it. You also can change, you can remove this 0.12, enable contact positional correction, and I think actually we can say, I think I can remove that. Maybe this one too. Let's see how stable it is. And yeah, and now it should work. If it doesn't, please take a look. Um, well, try to go along this code here when I'm showing you, or see the source code on GitHub. All right, let's go to the browser and refresh. Let's see if it's working. And yeah, it does actually. Awesome, cool. Well, and that's kind of a fixed joint, you know, it's still, yeah, it's still bending and so on, but at least it's trying to be fixed. Okay, and that's it for this episode. If you have troubles finding an error, don't worry. It doesn't matter if you skip this joint or you look at the code again. Um, yeah, it's not so important to have this one. Well, actually, no, none of the joints is really important. I think the more important one is the hinge joint, which we are going to do in the next episode. All right. Yeah. Sorry for the error hunting, and see you in the next one. Bye bye.